皆様、本日のウェビナーへご参加いただき、誠にありがとうございます。バイオサルジン北京のビジネス開発マネージャーチェンイホと申します。本セッションでは、弊社マウスモデル開発研究員のウー・ヤンチョン博士より、自己免疫疾患分野の最新動向と弊社の創薬支援マウスモデルについてご講演いただきます。なお、ウー博士のプレゼンテーションは英語で行われますが、画面に日本語字幕を表示しております。ウー博士はチューリッピ大学で神経科学の博士号を習得され、クリスパ技術を利用し、遺伝子研究や神経疾患のメカニズムを研究する経験を活かして、現在はバイオサルジンで自己免疫疾患のマウスモデル開発を担当されています。ご質問がありましたら QA ボックスへご投稿しお願いいたします。後ほどメールで回答いたします。それでは、ウ博士、よろしくお願いいたします。So, Dr. Wu Yancheng, over to you. Please begin your presentation.
Hello everyone, my name is Yancheng Wu, and I'm currently a model development researcher in the pharmacology and pharmacodynamics department at Biocelgen. It is a great honor to introduce Biocelgen's autoimmune disease-focused platform to you today. I sincerely hope that my presentation will provide valuable insight which may fulfill your research demand in the future. Today's presentation will cover three main parts. I will begin with a brief overview on autoimmune disease, followed by a detailed introduction to our in vivo animal models through Biocelgen's autoimmune disease platform. At the end, I will share some future perspectives and opportunities for how this platform may evolve and be applied. Let's start with the first part on the brief introduction of autoimmune disease. Autoimmune disease occur when the immune system malfunctions, attacking and damaging the body's own healthy cells, tissues, and organs. Common autoimmune disease include asthma, atopic dermatitis, psoriasis, inflammatory bowel disease, and some others. The pathogenic mechanism behind these autoimmune diseases are complex and involve multiple cascade reactions, including the abnormal activation of T and B cells, as well as the secretion of various helper T cells related cytokines, ultimately leading to the occurrence and development of chronic inflammation and tissue damage. From a market perspective, autoimmune diseases are a major global health concern. Key markets include Europe, Latin America, the Asia Pacific region, North America, the Middle East, and Africa. In 2024, the global autoimmune disease treatment market reached to $107.9 billion and is projected to grow up to $137.6 billion by 2033. Despite this growth both in China and the United States, the number of patients with autoimmune disease far exceeds the availability of effective treatments, indicating significant unmet medical need. The therapeutic landscape in autoimmune disease is highly diverse, including monoclonal and polyclonal antibodies, antibody-drug conjugates, some nucleic acid, and protein. Our humanized mouse model are compatible with a wide range of drug modalities, supporting diverse therapeutic strategies across multiple disease types. At Biocelgen, we have built a comprehensive portfolio of humanized models based on the pathogenic mechanism of various autoimmune diseases. This humanized model have supported many clients in conducting preclinical pharmacology, toxicology, and PK or PD studies. Now let's move to the second part, which is on Biocellugen's autoimmune disease-related biomice models. Our pharmacological and pharmacodynamics platform include a broad collection of disease models relevant to inflammatory, autoimmune, and metabolism disease-related models. This diagram categorized our models by organ systems, including skin, respiratory, gastrointestinal, nervous, and urinary system. The color coding indicates modeling data availability, in which green means pharmacodynamics data is available, black indicates modeling data is available, and orange shows that the model is currently under development. For today's presentation, I will highlight our modeling and efficacy evaluation methods through two emerging targets, which are TSLP for asthma and TL1A for IBD. I will also briefly introduce additional models from our platform to give you a broader view of our capabilities in pharmacological and pharmacodynamic research. Let's begin with asthma. I will firstly introduce the potential targets and corresponding animal models available in our platform to support asthma research. Asthma is a chronic inflammatory airway disease characterized by airway obstruction, airway hyperresponsiveness, and inflammation. These pathological changes are mediated by various immune cells, including airway epithelial cells, eosinophils, and T lymphocytes. In particular, Th2 cells play a dominant role in eosinophilic asthma by producing cytokines such as IL-4, IL-5, and IL-13. Our platform has established multiple asthma models designed to achieve different purposes in efficacy evaluation. The most common models are induced by albumin or house dust mites. In addition, we have established another specialized model targeting TSLP, where human TSLP is administered together with OR. To further enhance the model's utility for dual antibody testing, human IL-4 or IL-33 can be added. This last model is a unique feature of our platform. Evaluation parameters including the counts of neutrophils, eosinophils, and macrophage in bronchoalveolar lavage fluid, total serum IgG level, and histopathological analysis of lung tissues. TSLP is an emerging therapeutic target for asthma. Its drug, tezepelumab, like produced by Amgen, was approved in December 2021 and generated $970 million in revenue. We evaluated the efficacy of the tezepelumab analog using a human TSLP OI-induced asthma model in the humanized TSLP mice. Our data demonstrated that human TSLP OI induction significantly increased the number of mouse CD45 positive cells and eosinophil. Its ratio in mouse CD45 cells, the DARC in BLF, and total serum IgE treatment with tezepelumab analog significantly reversed these effects. Histopathological analysis further confirmed these findings. TSLP-OR treatment significantly elevates the score of inflammation cells, mucus production, and eosinophil infiltration in lung tissues. These effects were mitigated by treatment with teriflunomide analog. The experiment was repeated independently 3 times, confirming the reliability and stability of this asthma model. Autoimmune diseases, including asthma, are diverse and complex disorders that involve many signaling pathways. Targeting a single downstream factor often provides only partial therapeutic effects, while combination antibody therapies targeting multiple pathways are expected to be the future of asthma treatment. Recently, bispecific antibody targeting IL-4R alpha and TSLP entered a phase 1 clinical trial. To support this direction, we have established HIL4, HIL4RA, HTSLP, HTSLPR plasmids for preclinical studies related to asthma and atopic dermatitis. Using this model, we evaluated the efficacy of TSLP IL-4 monoclonal antibody combinations using TSLP OR HIL4 induced asthma model of HIL4, HIL4RA, TSLP, HTSLPR plus quadruple humanized mice. The 2-week study demonstrated that human TSLP or human IL-4 induction significantly increased the number of the mouse CD45 positive cells and eosinophils. Its ratio in mouse CD45 positive cells and total serum IgE. Treatment with the TSLP IL-4 monoclonal antibody combinations effectively reversed this pathological effect. This slide shows that his pathological results support the pharmacological data. Treatment with human TSLP or human IL-4 significantly elevated the score of inflammatory cells, mucus, and eosinophil. Neither tezepelumab nor dupilumab alone could significantly reduce this effect. However, high-dose combination TSLP IL-4 monoclonal antibody therapy substantially alleviated the pathological changes, demonstrating superior efficacy. Next, I will introduce the potential targets and animal models for inflammatory bowel disease in our platform. Ulcerative colitis and Crohn's disease are collectively known as inflammatory bowel disease. IBD is characterized by relapsing inflammation of the gastrointestinal tract due to abnormal activation of the mucosal immune system in genetically deposit individuals in response to luminal antigen. The current mainstay treatment modalities for inflammatory bowel disease include immunomodulators, biologics, and other monoclonal antibodies such as the anti-integrins and anti-interleukins. Additionally, promising results have been achieved in phase 2 testing anti-TL1A drug for the treatment of IBD. Many deals have been made for rise to an anti-TL1A therapy in recent years. To support efficacy evaluation study for TL1A, we have established the humanized TL1A mice, as well as multi-target humanized strains combining human TL1A with other relevant genes. By using our mice, WuXi conducted an in vivo efficacy study evaluating anti-TL1A antibodies. Administration of anti-human TL1A antibody, tulisokibart, and the anti-human IL-23p19 antibody risankizumab effectively improved TNBS-induced acute colitis. Notably, their combination demonstrated enhanced therapeutic effects. These results indicate that humanized TL1A, IL-23A, IL-12B mice are a powerful tool for evaluating in vivo efficacy of the combination therapies of anti-human TL1 antibody and anti-human IL-23p19 antibody. The combined administration of anti-human TL1A antibody and anti-human IL-23p19 antibody effectively ameliorated colonic pathological damage and reduce fibrosis progression in TNBS-induced acute colitis mice, with the combination therapy showing superior efficacy compared to monotherapy. Inflammatory cytokine analysis revealed that administration of anti-human TL1A antibody and anti-human IL-23p19 antibody markedly reduced the production of inflammatory cytokines in TNBS-induced acute colitis mice, with the combined treatment achieving a more pronounced anti-inflammatory effect. Our platform also supports efficacy evaluation using other colitis models, including DSS-induced acute colitis and T-cell transfer models of colitis. DSS-induced chronic colitis and TNBS-induced acute colitis models are also being developed. Our key evaluation metrics including clinical scoring, colon, lines, and the weight changes, and the histopathological analysis. We offer a broad panel of humanized mouse strain targeting different immune pathways relevant to IBD. This slide summarizes the availability strains optimized for preclinical efficacy study in IBD drug development. So far, I have introduced our modeling strategies and efficacy evaluation data for asthma and IBD, focusing on key targets such as TLSP and TL1A. Next, I would like to briefly introduce additional autoimmune disease models that we have successfully established and validated for efficacy studies. For atopic dermatitis, we have multiple modeling strategies available. Here we show one example data for modeling using human IL-31 to induce disease symptoms, followed by efficacy evaluation of nemolizumab analog. The core results for this model include ear thickness and scratching behavior. We can see that upon induction, both scratching counts and ear thickness significantly increase on both day 1 and day 4. Treatment with nemolizumab analog significantly reduced these parameters on day 4, demonstrating the model's suitability for therapeutic assessment. We offer a rich portfolio of humanized mouse model targeting various immune pathways to support pharmacological evaluations. This slide lists all the available strains of mice that are applicable for the drug efficacy study in atopic dermatitis. We have also developed multiple modeling strategies for rheumatoid arthritis. Here we show an example data using the collagen antibody-induced arthritis model, along with an efficacy study of methotrexate. The core index for this model is mainly the clinical scoring and histopathological changes. As shown, disease severity significantly increased on day 5 post-induction, while methotrexate treatment leads to marked reduction in both effects starting from day 11. We also provide an extensive array of humanized mice tailored to investigate different therapeutic targets in RA and evaluate the pharmacological effects. Here we list all kinds of mouse strains currently available for RA-related drug efficacy study. For the last section, I will highlight the autoimmune disease models along with representative efficacy data. These examples demonstrated the robust capabilities of our humanized mouse model for pharmacology research, and we can provide a broad selection of validation animal models targeting various pathways relevant to autoimmune research at Biocetrin. This table summarizes the current availability disease models together with the modeling approach we currently have. The core index for the efficacy study series, the optional detection readouts, and the models that we have tested for validation. In addition to our established models, we also have several other models that have been evaluated and confirmed will be developed in the near future, with some of them already undergoing first trial. We are very excited and confident for the new development and very looking forward to launch them into the market very soon to support future drug discovery efforts. In summary, to integrate this content and the capability of our pharmacology and pharmacodynamics department, we are able to establish animals that achieve different research purposes, including antibody therapies, CAR T-cell therapy, ADC, and more. Beyond autoimmune disease models, we also offer validated platform for oncology and metabolic disease studies, supported by a wide range of cutting-edge detection technologies. Biocetrin is continuously evolving to remain your top partner in preclinical research. We are committed to developing and establishing strategies for novel investigation, and we are pleased to collaborate with clients to bring new technologies into the evaluation of your promising discoveries. Okay, that's all of my presentation today. Thank you very much for your interest in our autoimmune disease models. If you have any question or need further information, please feel free to contact us. Thank you once again for your valuable time.
Thank you for your presentation, Dr. Wu. 本日のウェビナーを終了させていただきます。ご参加いただき、どうもありがとうございました。後日、録画と資料を共有させていただく予定です。お待ちいただけますと幸いです。何か質問や要件がありましたら、スライドに記載のメールアドレスまでご遠慮なく連絡ください。本日貴重な時間をいただき、誠にありがとうございました。